All right, welcome to Cristo Rey. We are actually located, to give you a precise location, if we look here at our note sheet map, hope you can see this on the camera. You can see on the paper it says Cristo Rey Geology Tour. We're right here on this little map, and it's right here on the edge of Mexico, New Mexico, and Texas. And you can see the Franklin Mountains right here above where it says PCB, and then the Sierra Nevadas mountains are right down here, and this blob right on this dashed line is Cristo Rey. And that dashed line is significant because if you remember from our time at the park last week, that represents the edge of the Chihuahua tectonic belt and trough, and that represents all the material that's located here in Cristo Rey. All this material right here slid up against the Franklins along this dotted line right here. So what we are looking at as we look off down in this trench for the railroad is we see a bunch of dark and tan material. The dark material formed in an ocean lagoon where there was very little wave action. Lots of organisms thrived in there. And then the light material is a mixture of sand and silt. So as the lagoon and the sea levels would rise and fall, the lagoon would go away and then it would come back. And all the material up here on the cliff and off in the distance, that's the Anapra sandstone. What do we usually associate with sandstone in terms of a place? If we're near the ocean, what would we think the sandstone would have been initially prior to being stone? Where do you usually go work on your tan when you go on vacation? A beach. So that's our beach. This is our lagoon. So what this tells us is that the ocean levels were rising and falling. So first it was a lagoon, and then the ocean level rose, and then beach up there. And these are all Cretaceous in age, from 140 million years ago till 65 million years. And the 65 million years represents when the dinosaurs from a meteorite attack, okay? And what's great is we'll see evidence of dinosaurs here later on. And so all this material here actually formed, not in this location though, it formed over 100 miles away in an ocean basin called the Chihuahua Trough. And so starting about 140 million years through 65, this stuff was forming. But then if we think back to our Laramide orogeny that we've studied and talked about, this stuff got pushed away from its original location to here. So it's actually, the rocks even are migrants. They even move from south to north. All right? They just didn't need any permission. It just happened. So here's our Cretaceous sediments right here, all nice and flat and uniform. Nothing exciting going on. There's lots of dead critters or sand and silt piling up like what we see over here off in the background. However, this stage B is our Laramide phase. Laramide, which started about 80 million years ago. That's when our squeezing started occurring and crumpling all of our nice uniform material. So this being said, if this is Cretaceous in age, which Cretaceous is 140 to 65 million years ago, this crunkling here tells us that we started getting squeezed before 65 million. We started getting squeezed closer to 80 million. And so that was our first main episode occurring. But then somewhere along the way after this started occurring, we started getting an intrusion here. And since I didn't have color printouts, you don't get the glory of the coloring. You can color that in later. We actually have magma intrude in and start to bulge up in the shape of what we can call a laccolith. which is a type of pluton, laccolith pluton. And its exact age, because the great thing about igneous material is you can date it radiometrically, and so its exact age is 45 million years ago. So we know that what the minimum age of everything can be. We know that all the Cretaceous, all the sediments have to be older than 45, which is younger than Cretaceous, but the Laramide started messing things up around 80 million years ago. And so somewhere between 80 and 65 million years ago, this started smashing, and then 45 million years ago, this bubbled up and created an Earth zit. But then, since then, all the upper material has been eroded away. So even though it looks kind of like a volcano right now, pan over there for me, would you? Even though where the cross is and everything at the top, it looks like it could have been a volcano. It's not. It's just an Earth zit where the skin just got peeled off. Okay? And so that's now what we're left with is in this bottom diagram right here. And so we're going to focus in on some of the processes. We're going to go look at this exact nature right here into the arroyo, and then we'll get into more details. Okay, here's our first indication, other than the piece I showed you in the parking lot, of all this material right here. What are we seeing again? What? Shells. So these are all polyspod shells. I'll spell that for you in a minute. So they're kind of like little oysters, okay? And this tells us we were in a marine environment and right in a reef, out of the wave zone, okay? All these dead critters, they would live, die, and just pile up like snowflakes. And so this is our first indication of what the material is made of. When we were up there at the parking lot, if it wasn't for that one rock I showed you, we just know we're in sedimentary, but we wouldn't know for sure real well. This tells us we're in a marine environment with all these shells that we can see right here. So as we move up through here, we'll see more of the layers of this Muletos formation. There's still some shells in there, but notice how the layers are not flat. They're tilted like my board, okay? They should be flat based on the diagram on the back here. When everything was first deposited, they should be flat, but they're not. That laramide squeezing affected these layers right here, and possibly even the intrusion. We can't tell yet which one is which based on what we know so far in the walk. But you can see these layers loaded with shells, but they're also got a lot of cracks and breaks in them. So it tells us it's been squished and mushed. All right, looky here. I was just here back in June. Everyone gather around. This white material right here is called calcite. And what it is, when we have limestone or carbonate rock, which has calcium carbonate in it, if it cracks and breaks, and then there's hot thermal water within the rock, especially if this used to be a marine material full of rock, it gets hot, it can recrystallize as calcite. But what happened here is we can see lines. See these blue lines? I drew these in back in June. There's lines in this calcite, and it shows us that there was rock grinding past this calcite, literally scraping. That tells us there's some kind of faulting going on. We don't know what yet, based on what we've seen, but we just know, another clue, faulting. We already saw folding, okay? So we already see tilting. So that tells us there's a lot going on already. And so all that gives us a clue. All right, as we're coming in over into this arroyo, right on the edge of Cristo Rey, we see a bunch of black rock and a big mess. Hopefully your eyes can start to make sense of some things on the light colored rock. If you look, zone in right here, trace the light colored material and see if you can make sense of the mayhem as we walk down into here. Sometimes you get too close, you can't see it. And that whole face is littered with. Here's the other side right here. So I'm in an arroyo and I can see layers going up on this side, down, and then back up. Here's our taco shell holding our meat that you all are standing in. Here's what it looks like in cross section, and it extends right towards you. But the arroyo has washed away the stuff that goes over and folds again and then back over. So we basically have folds coming back over again on top of each other. And that's because we had squeezing going on from these two directions. So it's like a carpet that's been smashed together from these two sides. Now the question is that smashing occurring due to just laramide orogeny like we have on our diagram, or is it due to the intrusion, or both? That's the big question, and that's what's hard to determine. But what we see here is, you notice all this rock is really black. It wasn't black over there by the railroad tracks. It was dark, but you had a lot of mixture of stuff. This looks more like it's cooked. Why do you think it might be cooked? What is possibly nearby that might have cooked it? Any idea? What are you sitting on right now? Is it the same color rock? No, it's light colored. And if you notice, it doesn't have layers or anything in it, and it's really hard. What type of rock do you think it is? Igneous, metamorphic, or sedimentary? Just take a wild guess.
Igneous.
Igneous. When it's igneous, when igneous comes up and comes into contact with pre-existing rock, what we call country rock, it can often cook it and bake it. So here's our original Cretaceous sedimentary rock that got heated and pressurized, and so it's been altered, it's been metamorphosed. And that's why it looks like a burnt cookie or burnt toast, however you want to consider that. And that's, all right, here we go. We're walking towards the scene of the crime. We can see this really dark material. This was what was over by the railroad tracks, the Moleros Formation. It looks very, very different. It's much darker, it's more solid. And as we come up here, we're actually on a fault line. So I don't know if any of you noticed, but right here, there's a bunch of lines, scrape lines. There's another fault. So we know that this material was sliding past. This side was sliding over this side, or this side was sliding under. They were going opposite of each other. And that's a real, it's called a slicken side. And that's real slick. And from the grooves that have been forced into the rock of it grinding past each other. So now the real big question is, why do we have this? We have this real dark material that we've been looking at, and all of a sudden, here's our igneous material that we were just talking about, that we saw in chunks down there. Look at this, all right along this edge. Which do you think was here first, the black material or the light white material?
Black.
Anyone else disagree or want to say, you think the black? What makes you think the black?
It is over the black? I don't know.
Well, which rock looks messed up and which one doesn't? If you can say.
Black?
The black looks messed up, right? Yeah. It's been altered because we've seen it from the other side where it was all that soft stuff over by the railroad track. Now it's all hardened and dark and it's altered. So that tells us that it was here first and it's been changed. The reason why I call this the scene of the crime is this is literally where the igneous material intruded into the Cretaceous sedimentary rock and contact metamorphosed. It heated, it baked and pressurized all this material, and it helped smash some of it, kind of like Jiffy Pop popcorn that comes up when you put it over a hot burner. It pushes up and away. And so this is like an earth zit, our andesite rock that came up and heated and smashed and folded some of this material, in addition to what the laramide orogeny has done. So what you see here, these white crystals are orthoclase and feldspars. The little bit of black is tiny, tiny bits of biotite. And we have a little bit of quartz, but it's really hard to see. This is an igneous rock that came near the surface but never made it to the surface, just like we see in this diagram right here on the stage C. And we can only see it now in stage D because all the material was eroded away off of it. The key thing is, what is the likely tectonic cause or source of the magma intruding in like it did and bubbling up? Well, the simple, most likely cause is our flat subduction, which we have in this diagram. So off the west coast of North America during the laterite orogeny, we had subduction going on, which was becoming Mexico and California. Remember, California and Mexico did not exist prior to 80 million years ago. It was the subduction that brought in all these microcontinents that formed Mexico and California. But down here in our diagram, you can see these little blobs of melt-off magma from the subducted oceanic plate. As that pops up, that creates our Earth zit, and that's what Cristo Rey is. Cristo Rey is magma that came up through the crust and bubbled up, just like we have in our diagram right here. And so 45 million years ago is the date of that coming in and cooling. So it could be 44 million years, just because from when it initially came in. But it's the tectonic source is the subduction off of the laramide orogeny occurring. And that's our well, first of all, what you're standing on again is that sandstone siltstone layer. Okay, this material is tilted down this way. It should be flat. It's not flat. It was originally flat. It's been tilted, but during deposition, here we have our, again, another cross-section view. Here's our beach, silty sandy beach. Here's our lagoon shale, and then back to silty sandy beach, and then more little bit of shale, so it alternates. So that's our cyclothem that is telling us, as we see over there even better, and even over in that big face, the ocean was rising and falling. So if you were going to be walking through along the coast, what would you want to be walking in? Lagoon or silty sandy beach? Which would be the easiest to walk on? The sandy silty beach. So animal activity would be most likely where? In terms of walking wise, it would be on the beach. So if we think in terms of dinosaurs walking along, we're standing on what used to be a near flat beach. But as you just noticed, and it's gotten a little worn out, right here is one of the best preservations of a three-toed dinosaur track right here. And if I bring the note sheet, so if I orient the note sheet patterns, these patterns right here, these three-toed prints, are just like this. And they are anticipated to be a minimum of 9 feet tall. Kind of like a velociraptor in shape, but without the claws. And so this footprint is going towards Georgina, but most of the other footprints are going left and right. All these little humps, and so here's another one right here. Here's another real good one, a three-toed one, right there. So you get a sense of the scale of how big they were. So it's like 4 of my feet, okay, in terms of size. And there's another 3 toes, right like there. Most of the prints show them going basically north and south, along parallel to the river pattern. So this is our significant trace fossils from our dinosaurs, and these were plant eaters, not predators, because we don't have the claws that are evident in here. And so here we have, so we had to have the rising and falling of the ocean to create this beach and lagoon scenario, but then we have one more thing going on. So first we have all this beach and ocean, we have dinosaur activity that everyone can hoo and haw about, but the significant activities were, first we have squeezing. Here's our laramide orogeny squeezing on our diagram after all this stuff forms, okay? And it's during the laramide orogeny we start getting all these big folds. And look at this, it's all tilted. We can see right here with the manual and the outcrop over there, all the beds are tilted down to the right, which is to the southwest. So this is one side of a giant fold during the laramide squeezing. But then as a result of subduction going on from the laramide, we get the intrusion of andesite here in our bubble of magma, which then adds more folding, and metamorphic rocks metamorphose some of this Cretaceous sedimentary rock that's over there. But there's one last stage. Look straight over there on that cliff face, and what stands out beyond the layers? We know we can see layers that are tilted. What else do you see going on? Exactly. So think of a big piece of cake, right? And if you want to eat that cake, you usually got to have a knife, right? And so it's like someone took a knife and cut right through it. And if you notice, one of the thick layers about midway through, you have a real thick dark layer with a light layer and then another thick dark layer. So it's that light layer in between those two dark layers. It's cut, and then the side on the right goes down. You remember from physical geology, so the right side would be your kind of your hanging wall. It's a real steep fault, so it's hard to say for sure, but that would most likely be your hanging wall. So if the hanging wall goes down, you remember what type of fault that is? If you think of a bunch of books and a bookend, you pull the bookend out and one of the books starts to slide down, what type of fault would that likely be? There's thrust, reverse, normal, shear fault. What do you think that would be? Normal fault. That's why I'm a geologist, because I tell my wife all the time, all my faults are normal. Stop trying to reverse them. And I get paid to have faults. So that's your normal fault. So now from what we just did in our lab, what type of stress or tectonic setting has mostly normal faults? We have two different types. We have convergent and divergent or transform. Which one of those three is mostly normal faults? So the hanging wall's going down. If something's going down, then which environment? What's the last tectonic episode we have here in going on right now? We had squeezing going on first during the laramide. What's the final? What's that? Divergent, which would be called, what do we call? We have the river. What's the name of the river? Right here? Rio Grande. So what's our tectonic spot? It's called the Rio Grande something. And it's divergent. It's pulling apart. What is that called? Rift. That's our key evidence right there of rift going on, even if we had no idea that the river. So our final episode is the Rio Grande Rift, and that normal fault coming through gives us evidence of that.